Hi everyone and welcome to the session. So I'm very excited because this is the first session in a long while after the December break. So we'll be covering a paper that I found quite inspirational. It's called Supervised Reinforcement Learning. Yeah, I know the name sounds a bit weird because we are used to either supervised learning or reinforcement learning, but this paper by Google researchers tries to combine the benefits of both into one single learning method. So they call it supervised reinforcement learning, where you learn by having reinforcement learning reward signals as well as traditional supervised learning. So how do they do this? Yeah, that's what we'll be talking about today. So essentially, I can tell you roughly what it is that it uses a model answer from an expert and break it down into steps. And then basically at each step, we will use some reward from each step to condition the learning model to try to match the output for each step. So like if let's say for example each step consists of an action, like the action is move up or move down to navigate a maze, then you try to match the action to the expert trajectory. Or in this case for large language models, we are talking about like solving math problems here. So we try to match the output of for each step. Like first, we should add 3 plus 3, that the output for the first step. You try to match that to the expert model. So yeah, enough of all this. I think the paper itself is a pretty simple one, but I found that the explanation is a little too complicated. So I have my own visuals here to help you understand what it is. So essentially, the first 4 slides you will see later, it will cover everything that I want to talk about today. So think of yourself as this little ball over here. So if you look at this ball, and your goal is to get out at this part of the maze, and you have absolutely no idea how to do that, right? So you could explore like, oh, I should go up, I should go right, but I see until here only. I don't have the full picture of the whole maze. And honestly, if I were to just go by gut feel, maybe I'll go here, and then after a while I like, hey, I'm stuck. What should I do? Then you could try to explore other options here. Then you could try to explore other options and so on. And then eventually you might conclude that, you know what? It's too tough for me. I can't find the way out. This problem is too hard. I'm not going to solve this maze anymore. Yeah. So this is typically what happens when you put someone very junior to do a very difficult problem. Like for example, if let's say someone is in primary school who only knows how to do like maybe 3 plus 5, that kind of thing, simple addition, you suddenly ask them to do sine x, sine 90 degree times cos yeah, that kind of thing, to the power of 4 or something like that, So if let's say I were to, this is your knowledge base and I ask you to do this, um, it's something like you navigating this huge complex maze. You try your best, you bump into walls, and you can't find your way out. So essentially, this is not a good solution, right? This is not a good way to train this ball. Like you can't just dump it in a maze that is so difficult and ask it to find the solution just like that. It's almost impossible to find it. Oh, but what if I change the maze a bit? Okay, instead of just giving you like some reward at the end of the maze, I put some rewards in the middle here, You see these light bulbs here? These light bulbs are your rewards. So once you are over here, you're like, hey, there's a glimmer of light here. Maybe let me investigate. Oh, I found a light bulb. Wow, I'm on the right path. Then over here is like, hey, where am I? Oh, this part doesn't look very bright. It's a bit dark. This part's here. Nope, maybe I shouldn't go here. Yes, I should head here. Oh, yes, I found another light bulb. And so, yes, I found another light bulb. And oh, I solved it. So it's somewhat like, a teacher giving some guidance to your students, say, hey, do a little bit, do a little bit. Yeah, you're getting on the right track. Continue, continue. So there's some form of some intermittent feedback that helps you to guide yourself along the way to reach the end goal. Yes, Robert, you want to say something?
Yeah, how does this differ from Micromouse, the competition that they were using back in like the 80s? They started doing this concept of solving puzzles or mazes, right, with autonomous robots. And then it was a competition. So I was wondering if this is like the same trajectory.
Oh, slightly different. I mean, the micro mouse competition, usually you have the grid and then maybe you start in the center and you want to find your way to the center. So the end goal is here. And then what the mouse will do is they will explore almost everything here. And then it will have a memory of the whole path and it will just dash towards the path. So micro mouse, explores everything. Yeah. But in this case, we have this problem here that we may not be able to explore the whole maze.
Interesting.
Yeah, so there are some problems that are just computationally infeasible to derive a perfect optimal solution. Like the micro solution is optimal. You have like I think 2 to 3 minutes to explore the maze first before you dash to the center. So it is optimal in the sense that you really cater into account how fast you turn, how fast you go straight, how fast you rotate and so on. Yeah, so this is already solved mathematically. This kind of problem is like I ask you to solve an open-ended problem that, people haven't really solved yet. Like for example, in math, solve the 3n plus 1 conjecture, which is called the collapse conjecture, which it has no proof because like any number they say if you start from basically you can search 3n plus 1. Like if it's odd number, then you do 3n plus 1, and if it's even, you divide by 2. Eventually, you start with any integer greater than 1, you end up with 1. Yeah, so that's the conjecture. Yeah, this hasn't been able to prove yet. It's somewhat like navigating this maze, you don't have any idea how to get to the end. Like, I can give you the example in the next slide as well. Like, the next slide is about like show that, we have reached AGI in by 2030. You can't know because there's just too much things to do, and you cannot possibly explore every branch.
Makes
Yeah.
sense. The way I look at it is like what you call is like the visible mass versus the invisible mass. And then you match it from like a constraint based to a policy. So like these example, the light bulbs, right, would be your policies and your constraints is your like your map, right? And the invisible mass is what you can see and the visible is what you can't see.
Yeah, definitely. Yeah. So in actually every problem solving domain, you kind of want to like first kind of narrow down your scope so that you can explore more in that area. So I guess that's your visible mass, right? But you must smartly, throw away the invisible mass, which is like the stuff that you don't want to explore. Because if not, if you throw away the solution here, then that's too bad. You won't solve it. So it's very difficult to solve these kind of problems because you can't brute force everything. You can't search everything. And that's where, the guidance matters. If you already have someone who has solved the maze, and they just drop like nuggets of information like this light bulb here, that you will actually greatly increase the chance of a subsequent person solving the maze. And that's exactly what supervised reinforcement learning is doing. An expert will leave traces behind, and you follow those traces, right? So these are the light bulbs here that you see in this maze. All right. So this exactly is trying to learn, like if you were to learn a very difficult problem, chances are if you just query your own knowledge base, you can't solve it. Like, for example, if you want to solve a trigonometry problem, but you only know addition, you can't do it. It's like you try your best, but you just don't have the knowledge to do it. Yeah, and that's exactly like you are this ball here, and you're trying to solve this maze here without any guidance at all. All right? You can't solve it. It's like, for example, asking someone to prove that AGI is not possible by 2030. No, what exactly is AGI? Maybe we call it like can do anything a human can do. And you can't really you can't really visualize how to get through that because there's just too many factors in place. Right? But if let's say I could say that, hey, I have some intermediate output here, and this output here maybe is AGI is not possible by 2025, then that's okay because we can actually like do a easier to predict what will happen in a year, and this year has already passed by. So so I just put this infographic here. I created it. It's meant to be a laugh because if you know me, I don't believe in anything called AGI. I'm with Yan LeCun here. Artificial general intelligence, where the AI can do anything a human can do. I think that's a bit. Oh, sorry, AGI. Some people define it as the AI can learn anything. I think that's too broad. Like, and any intelligence has its constraints. It's optimized to that particular organism. So I don't really like the idea of AGI. I mean, like something like if you want to say we can replicate what a human can do, then I take that definition better. But anyway, this comment is just to show you that if you break a problem down into simpler parts and you give guidance for each part, you might be able to solve it much better than just giving it the full problem itself. So this is nothing new actually. This is like in mathematics, they like to break it down by like solving a problem by parts and so on. This is very, very standard computer programming stuff also. Like we always break a complex problem down into parts. Like, when we do divide and conquer, for example, in computer science, we try to break down the problem into smaller parts and solve each part separately. There's also other ways to do like math, like hypertree proof search. You can search the paper by meta. So you're also solving the problem by parts. Okay, but what's the difference here? The difference in this paper is they made the problem a bit easier. They actually have an expert signal, all right, which is this light bulbs here, which are the light bulbs here. So yeah, I think that's about it for what I want to cover today. This is in the gist of it. If you just have an expert give intermittent signals, your model can learn better. And essentially, that's the whole paper. But of course, I don't think you are satisfied with that. Let's go more into detail about how they do it. All right, so this is how it looks like. We can translate the maze case into a large language model input and output. This is how it looks like. For example, your prompt could be like evaluate the result of step one, two, three. You say your step one, two, three. This could be a math problem like evaluate 2 plus 2 times 4. Yeah, something like that. So maybe your step one here will be 2 plus 2 equals to 4. Then the step two will be 4 times 4 equals to 16. Yeah, here there's only two steps, but you can translate this thing into any problem that you wish that has multiple steps. If you want to talk about agentic systems, you might want to say do a Google search on LLMs, then write an essay, that with citations. So these are two steps that you do. So this is quite conventional. These are quite conventional stuff. Or you could do something like, search for nearest hotels, rank them by price, and then recommend me the best hotels. Something like that. These are three different steps, and then you have three different outputs for each step, and then finally you have like the aggregated answer. So something like this is what an LM agentic system would do. And the thing is, if you were to put as a training this as the prompt, and then your output here would be very, very long output, very long specific output to the prompt. Wait, can you see a slight issue here? The slight issue is how do we generalize, right? Like we learn exactly this the output for this particular prompt. But what if we want to change hotel to maybe garage, or we want to change rank by price to rank by star rating? So different kinds of ways of changing the steps would lead to the output change. And it need not just be a simple copy and paste and replace kind of thing. The entire logic might already change just because of this one step. So it is very tough because you are sort of like memorizing the entire model answer to a problem. And if you have done exams, right? Like if I were to give you a very difficult problem and I ask you to memorize the solution, then I give you another difficult problem and I ask you to memorize the solution for the other problem. And then suddenly I just say that, hey, this is my third problem. I changed one variable in the first problem and and ask you to come up with the solution. You may not learn enough to help you to do that. Yep. You may have just memorized it without learning how to generalize. And that's exactly the problem that the researchers note in the large language model, right? If we just train it like this, just for the input and output, the prompt, you train the prompt and then you try to let the large language model output exactly this sample output, you may face the problem that the model just memorizes it without really understanding what it needs to do when something changes, right? Yeah, pause here for what? Robert, you want to say something?
Yeah, are all prompts downward descent? Like, are they all descent based?
Sorry, can you
Like
repeat that again?
are all the prompts, like for an example, step by step downward descent? Like they're all downward like gradients, you know what I mean? How they're saying instruction step one, step two, step three.
Yeah,
Is that the
very
only
likely.
way that we
Yeah,
know prompting?
Very likely, the prompt itself will already contain the steps in sequential order. But from some math questions, you don't have the steps, so you kind of need to think of what steps to do. Like for example, the question could ask you to, like, find the maximum number of houses you can buy with this amount of money. Then you have to kind of formulate. Oh, step one, I need to check which are the houses available. What's the cost for each square feet, that kind of thing. Yep. So you kind of need to think of the steps yourself. So I'm just giving you the prompt here in a very explicit way to say step one, step two, step three, for a better understanding. But not all the time the prompt will give you the exact steps. Sometimes you need to infer the steps. Yeah, so I hope that answers the question. So you kind of need to, from the question itself, infer the steps to solve it and do the steps and solve the question. Yeah. So again, this kind of leads to memorization, and you'll see in the results later that if we just do this thing called supervised fine-tuning, where you try to memorize the answer to each prompt, it actually leads to worse performance in the base model because exactly of that reason. We overfit too much to the model answer. We haven't really learned why this step is necessary, or like why do we even or how do we even do this step? Like we haven't really generalized that because we are trying to learn a whole thing to a whole thing. Like you're trying to learn too much. Okay, so the best kind of teachers are not teachers who ask you to memorize the model essays and stuff. They actually teach you the rationale behind why each step is being done. So you are free to mix and match the steps yourself for other problems. In fact, when I teach math to people, I do the same thing as well. You collect a list of tools and then you just mix and match the tools based on what is necessary. And we don't learn like we don't memorize model solutions. Like I was in Math Olympiad last time also. Like we don't memorize model solutions to every single problem. We kind of understand why do we use this particular tool for that problem, so that in the future, when something happens, that changes the problem, we might change the tools and then we eventually reach a similar state and you can use the same tools again. Yeah, so it's very, very important to learn in this thing called learn in a modular fashion. All right, this is very, very important. In fact, if you want to be a teacher, I think this is quite important because I think memorization will only take you so far. If you truly want to generalize, you need to know why you do each step. Then you can apply it to different problems. All right. So, Robert, you also asked for REPL, the like coding, right? How will it work for coding? All right. So basically, if you were to do coding, then it will be something like um, print out the first five prime numbers or something like that. And maybe your step one would be find a way to generate primes. Yeah. Then after that, look through and get first five primes. And then, the last step could be print out the first five primes. Yeah, so something like that. The the steps change a bit based on the domain, but essentially you still do things in a sequential manner like that. So I hope that answered the question. Like, how do you do it for REPL, like a programming kind of tool? Essentially, you break down the problem into sub steps and then you do it. Yeah. So yeah, this kind of how coding agents work as well. They kind of break your request down into steps and then do each step. All right, let's move on. So how can we make the problem easier? You know, let's try not to ask the model to output too much. All right, let's try to target a very, very specific and modular output. So I don't need the full solution now. Okay, I just need the LM to output the next step. All right. So I quite like this idea. All right. Um, I don't know if you all have played Go before. Go is the black and white stones, and then you have a board. Who here has played Go before, by the way? This is the black and white stones. Then you have the black stones. If your black stones surround the white stones, then you eat up the stones. Then in the end, you just calculate who has the bigger area. So this was used in software like AlphaGo. Who here has heard of Go before? Okay, no one. Okay, I think you should have heard of
Definitely,
something like
definitely heard of it. Definitely heard of it.
yeah.
Studied it.
Okay, so in Go, there's this thing called Go, which means the next move of Go. So I quite like this idea. They basically build an entire board of stone positions, and then maybe they'll ask it'll be a problem. Like for example, if this stone position is like that, it is very, very basic, all right? I mean, like let's say you really, really want to surround this piece. Okay, by right you shouldn't eat this, okay? Because like eating this piece doesn't really help much. You should pressure this piece to go somewhere else. Then you can get all your black color stones outside and you get influence. But let's suppose your aim is to eat this white piece up. So Zimego asks you, okay, given this board state, what should you move next? All right, and if you want to eat this white stone up, then you should move here. This is your next move. They can eat up the stone because you surround the white stones on all sides. So given a board state, what is the next best move? Okay, given the board state, what is the next best move? That's the question we ask. All right. Same thing if you talk about stuff like chess. You can also do the same thing for chess. You have a chess board. Let's say you have only like, okay, I'm just going to draw a simplified chess board with like 3 squares because it's, so let's say you have a queen here and then you have a king here. Maybe the king, I put K. This is your king and this is your queen. All right, where should you move next to checkmate? There's something like that. Yep. So the answer is you should move your queen somewhere here. I mean, like then you'll win because the queen will checkmate the king. All right. So this is something like you want to find out, given a certain state, what should I do next? What's the best move I should do next? Okay. Actually, if you think of life's problems, right? You can ask yourself that, and like, given my current situation now, what should I do next? All right. So you just okay. I know that people say you need to do planning, long-term planning. You need to do tree search, find the best move, and so on. But I know sometimes intuition helps a lot. Like you don't really have to plan out too much in advance. Like the comic books like Sherlock Holmes try to do everything in the head, and in real life that's not practical. Okay, that's not practical. Why? Because real life changes, like things change. You can't plan a 1 year plan and then say that, hey, I'm just going to do this 1 year plan the whole time. It will change. So more often than not, just simply doing the next best move available to you is good enough to carry you through life. Yep. Yes, Derek, you want to say something?
No, I was going to add on to your comment about the chess planning and actually at most chess spots. So the actual approach they do, they start off like with stockfish. They start off with a neural network, which is like the instinct they use to get an initial best move, and then they run tree search on that initial best move to optimize it to the absolute best move that the model can go into in what is it breadth depth search in the tree search or in the sorry in the solution space search. So technically both are correct. So planning and instinct are both correct, but the optimal approach in chess planning is to start out with a neural network, which is your instinct, to start off with instinct, and then you use that instinct as an initial good step to find the best chess move based on planning ahead.
Yeah, definitely. And actually that's because the world model that we have for those chess engines is perfect. You know for sure that if you do a certain move, you end up with a certain board state. What I'm saying is
Hmm.
that in real life you may not have that world model. Yeah. So
That's true.
maybe just a next move is enough. You could do some planning, definitely. It will help to increase your accuracy of your next move. But sometimes planning too much is detrimental. So, most of the time, if you just know what's the next move, that's enough. That's enough to get you by quite I wouldn't say optimally, but you'll be good enough. Yeah. So I think this is the way that we break down complex problems into sub problems. And if you can solve each sub problem well, perhaps you can solve the whole problem if you combine the series of sub-problems. So this is how we do it in large language models. You take a prompt, a very difficult prompt that you have no idea what to do, and then you just say, hey, just output the first step. Okay, this is the first step output. All right, then I go to the next prompt. All right, this is like, hey, you are given the output of your previous step now. What should you do next? And then you output, oh, step two, I should do Y, Y, Y. All right, then let's do that again. Now I have my partial solution x x x y y y. What should you do next? Oh, step three, z, z, z. Okay, great. Now I have step two and step three done. Output next step. Oh, the answer is just A. Done. I solved my problem. So just what's the next step? What's the next step? What's the next step? You know, just asking you to output the next step. Eventually, I might get the answer. No, that's if you solve the problem. All right. So a very big caveat here. If you solve the problem, you validate the first few steps. Okay, what happens if you don't solve the problem? Then your whole trajectory doesn't solve the prompt, doesn't solve this task. So you may have to discard it. Right. So that's why it's very important that in this method of supervised reinforcement learning, your expert needs to solve the problem. So,
Would
this, sorry, let me finish this. So this way of SRL that they did in the paper won't help you to break new boundaries. It will do some form of teacher training to the student to let the student be better able to mimic the teacher in some sense. Okay, later in the discussion, I will describe some approaches I think would be beneficial for exploratory learning, even beyond the frontier of knowledge that we already have. Okay, yes, Robert, you may speak now.
Sorry. No, it's an everyday problem. I mean, half the problem is related to now like data quality, right? And so you're saying that no matter what, the outcome is determined based on the quality of accuracy, right?
Yes.
So the first step has to be accurate, or other steps are always going to fail.
Okay, that's not exactly true. Because you might have the step two to correct the step one.
Oh,
Yeah,
that's exactly right. So then that's planning, though, right?
yeah. So in these sub steps, if they realize the previous steps are wrong, the next step can actually do correction. So this is like the thinking models where you ask it to reflect on the earlier parts. This step could be a reflection step. So it's not necessarily like once your step one is gone, then that's it. You can actually still correct the problem. Yeah,
Okay.
but of course, once you correct the problem, you don't want to, do the reflection and put that in the training data. You want it, maybe you can ask the expert model to summarize the steps without the reflection. Because like imagine if you do a wrong step and you train that to your student model, then your student model will purposely make a mistake first. Then reflect on the mistake. You don't really want that to happen, right? So you need to clean up the data a bit, make sure the steps are all towards the goal and not like going away from it. Yeah, so you can do that once you solve the problem. You can use the benefit of hindsight and clean up your steps. So once we do the teacher-student training, we kind of don't want to do the reflection. Although actually, it might be quite a curious thing to include the reflection in. Then you make the purposely make the student make mistakes so that it becomes a bit more versatile. Yeah. So I mean, it could work both ways. Like, but I think if you want to train like this step-by-step approach, you don't purposely give the wrong step to the student. Like you typically would give the right steps. So yeah, I think there's still some room for error here. If you have a wrong step or wrong output, if your subsequent steps catch it, it still can save the day.
Sorry, can I chime in here?
Yeah, go ahead, sorry.
Uh, okay, first, I think this remind me of like when you learn like last time in school, right? Sometimes um when the teacher is gonna teach a very tricky problem, your teacher might present you with a very common mistake. So as a contrasting examples, I wonder if reflection can serve the same purpose.
Yeah, possible. Yeah. So there could be some questions where you start off with the wrong state and you ask your model to reflect back to the right state.
Yeah, so that still serves as some very useful teaching signals, right?
Yeah, definitely. Yeah. So
Second,
yeah,
yeah,
please continue. Yeah, continue.
no, it's another thing you can finish. Yeah.
Oh no, I just wanted to say that in this paper, they didn't actually say that the expert model needs to reflect and clean up. They basically just use an expert model, come up with the steps, and then use those steps to train. And I believe the expert model can solve everything. So that's why it's yeah the reflection pathway I don't think is really used in this paper. Although I think it could be quite interesting to code it in as well. Like I'm not sure whether purposely putting in the errors would help, but but maybe you could have a starting state where there's some error and then ask it to reflect back. I think that would help. Yeah, rather than giving it the wrong chain of thought.
But
I mean,
Sorry,
even
John, could I? Sorry.
Maybe so you say first.
I'm gonna I'm
Yeah.
gonna
Yeah.
I'm gonna chime in first. Really quick on
Okay.
the expert model. Um, I've read through the paper. I could be incorrect because I was briefing it quickly. I was under the understanding that they used human experts to do the step-by-step breakdowns as for the training data, and then they had the model train on the trajectories written by the human experts. Am I incorrect on that? Was it an expert model the whole time?
I think it was the expert model. So actually to me that's not a big thing because like expert model or experts, the main thing is you just need the expert trajectory. Yeah, but
Right.
I believe they
But
use
the
an LM for
okay.
it.
Okay, I'll read the paper again. Okay. So it's an LLM producing all the step-by-step trajectories.
Yes, yes, that's what I read in the paper.
Okay, okay. I'll reread.
But I believe the LM has been trained by humans, so you might be right in some way. They have been trained by humans in some pre-training data. Yeah.
Probably. We'll see.
Yeah, sorry, please go ahead.
Second point is I remember from DeepSeek R1 paper, the reflection aha moment. They they
Yes.
they call it immersion. So I think in their training pipeline, they did not use reflection, right? Otherwise, it's supervised. It's not immersion.
I mean, it depends how they train it. If they didn't train for reflection, but reflection come out, then that could
Yeah,
justify the
yeah.
aha
I mean, the
moment.
way they
Yeah.
present it is immersion. So it also can learn to reflect without you explicitly giving examples of reflection. Yeah,
Yeah, possible.
yeah, that's all my comment.
Okay, anyone else? If not, we will move on. All right, let's move on then. So yeah, you can see that there's step-by-step approaches have quite a lot of flexibility here. So that's why it's it's like agentic systems with many different steps kind of have a lot of versatility in them compared to just a single shot output. Right? So, you know, let's just take an expert model, ask it to output in a certain format. We slice the output format into different steps. So essentially, we take a trajectory. So let me just summarize this here. We take a trajectory, a solution of the solution, and we do step-by-step training to match the next step output given the context, given the earlier context. So you can see given one very long prompt, very long output. Like for example, here there's 3 steps and 1 answer. You can split into 4 training problems. You can say, hey, this is training problem 1, training problem 2, training problem 3, training problem 4, which denote like what should you do for the next step. And this actually helps the model to learn better how to output the next step. Okay, because no longer are you penalized with a long essay of token by token matching to make sure you match exactly word for word how this output is. Now we train it to output word for word on a single step. So it's more targeted training. Okay, and actually the training itself, I think you could use supervised fine-tuning as well. You could break this problem down into these steps here to do fine-tuning. In this paper, they use reinforcement learning. Okay, how do they do that? Later, I'll explain how they do it. But basically, they treat each output and do it with some form of rule-based way of getting a reward. And then you use the GRPO, the Group Relative Policy Optimization. So they use GRPO to train the, the RL part, right? So this GRPO is a great way of learning. But I actually think that you may not even need the RL part. The main thing is you just need to have a fine-tuning way to learn from each step. And regardless of how you do it, RL or supervised learning, yeah, as long as you learn, it should work. Yeah. So this is the gist of how this SRL is. You just break the problem down into steps, you learn each step. And the question to ponder, which we'll discuss this later, now we have an expert trajectory. Can we not have an expert trajectory and still learn all this? So we'll discuss that later. Okay, let's move on. So this is the results, all right? So they tested it on some math data sets uh, and other data sets. Also did some programming data sets. And you can see that this is the baseline model. in gray. All right, this is the Quen 2.57b instruct. And the surprising thing is if you were to use like 1000 good problems and you fine tune on those 1000 good problems, you notice that in general, if you do a fine tuning to that particular data set, so the base model is not trained on those data sets, or rather, it's not purposely trained to these data sets. But if you take the base model of this Quen 2.57b, you purposely train it on that data set itself, like the AMC, you notice a drop in performance. So this, I believe, is the solve rate, all right? And you can see that the base model itself is actually not that great. I mean, it only solves like 50%, and I wonder how it will be for better models. But I guess for better models, you won't see such a big difference because if the base model is already quite good, once you fine tune, it shouldn't drop that much. But you can see there's a huge drop here. Like you can see that over here, like when they did supervised fine tuning, like even with reasoning and stuff, you still see a drop in performance, which means that just by learning from traces alone, all right, reasoning traces alone, um, it faces the problem that you overfit to the reasoning traces, and sometimes you use the wrong reasoning trace for something else. Okay, but once they use the RL method, so RLVR is basically trained from trajectories that are successful using GRPO. So the reward is only at the end. You can see that RLVR is not too bad. In most of the approaches, it's actually doing quite well. I mean, on par or sometimes even better than the base model. But what they have found out is that if you use this thing called the supervised reinforcement learning, okay, you can see the SRL is similar to RLVR. It's actually better, actually, the orange one. But the best is if you do supervised reinforcement learning to learn step-by-step approach. Then you give it RLVR, which asks it to learn from only the successful trajectories. Because of the SRL training, it's able to do step-by-step planning better or step-by-step output better. It gets more of the final rewards. And so this RLVR training is effective. You can see there's some gain of using SRL to RLVR for some. Okay, this one is not really. Yeah, but for some, yes, but for some it's also going down, is it? So it's a bit inconclusive, like whether or not you can learn from RLVR even after you do SRL. Okay, because if suddenly this, let me just rephrase this. SRL is a step-by-step rewards, but RLVR, reinforcement learning verifiable rewards, is only end outcome rewards. So you only get the reward if you get the answer correct. So there's some benefit of doing step-by-step rewards, and then after that throwing you in the deep end and only giving you the reward right at the end. But in my own honest opinion, there's no need to do RLVR. Like once you finish your SRL, why not just stick to it? Like this is good enough, right? Like if you look at the graph here, the orange and red perform almost the same. Maybe only this part here there's like a sudden improvement. Yeah, but the rest look about the same. In fact, some even drops after you do RLVR. So why not just do SRL? That's my opinion. So, and there's also one other thing I want you to look at is this dark green line here. Once you do supervised fine tuning, which means you overfit the model into the problems itself, and then you do RLVR, which you only reward successful trajectories, right? Notice this dark green bar is horrible. It's like one of the worst performing, these dark green bars. Yeah. So it shows that after you overfit the model into the training problems of that particular data set, you actually get a worse off performance if you do the end outcome shaping. Then if you just do RLVR directly without doing the SFT. So you see, if you just do if you just do RLVR at the start, it's much better. So the conventional wisdom, we should fine tune our model to our data set, and from that data set, we can give it the knowledge it needs in order to solve a problem. No, sometimes this fine tuning actually harms the model because your pre-training data is spread across a lot of different domains. Suddenly, I want you to focus on this domain. You might be narrow-minded. You might think only in that domain. And I always like to say this: fine tuning to a data set is something like doing a PhD because you kind of only zone in on that problem. And that's why, although I did my PhD, I try my best to keep open-minded, try to read other things. In addition to computer science and machine learning, I try to read stuff on psychology, spirituality, and so on to keep my mind open. Because if you get zoned into only a particular way of thinking, you will never see the full picture, right? And in this case, the SFT even harms the model. So yeah, I don't think fine-tuning on a data set is actually the best way to get about doing things. Okay, there must be another approach, and maybe that approach is this supervised reinforcement learning. Okay, I'm going to pause here for a while for any questions, comments.
Yeah, I have one.
Yes,
I have two.
go ahead, go ahead. Yeah.
First is you see the SFT followed by RLVR. So this strike me as very similar to how the typical reasoning model is trained, right? If you look
Yeah,
at
yes, yes, yes,
yeah,
yes. Mm.
but then here it didn't work. I just find it very intriguing.
Yeah, maybe they fine-tune too much. I mean, there's a lot of hyperparameters that you need to tune. And this is using a Quen small model. So maybe small models don't adapt to distribution shifts that much as a big model.
That means depend on your setting. This pipeline sometimes may work, sometimes may not work.
Yeah, so the limitations of this paper is that they'll need it on one model, which is the Quen 2.57b, and we don't really see how it works on other models. So it might just be a quirk of this model.
Oh, sorry, what does the outline mean in the parentheses?
Oh, actually, I didn't really read in detail, but just by a gut feel, reasoning probably is the full reasoning trace outline, maybe it's a summary.
I see, I see.
Yeah.
Okay, that's my first. Second is if so if I understand correctly, your view is that if you want to improve performance on certain benchmark, the conventional wisdom is just to train on that task or that data set. But here it shows it has the opposite effect. So am I correct? Can I say that when people commenting on how Frontier Lab LLMs keep saturating benchmark, they say, oh, they just train on the benchmark. Actually, that's not the case because if you train on benchmark, it gets worse.
That's for this model. Yeah. So I think if you train on benchmarks long enough, you might be able to solve. And this benchmark training is a bit different from conventional benchmark training. They only use 1,000 examples.
Right.
Yeah. So it's not the full benchmark. They only train on 1,000 samples. So yeah, I believe they train on the S1K data set, which is the 1,000 samples. So if you actually train on I think if you only train on if you train on the full data, I'm sure your model will overfit and you will do well.
Wait, but I remember suddenly I remember there's a tiny S1 paper, not sure if you remember from Stanford. So they show that with a very small, high quality data set, they are able to improve their reasoning model performance by a lot. So they also did not extensively train on some very large data set, but they managed to improve their performance.
Yeah.
I
So
can
as I said, treat these results with a pinch of salt. I mean, it's only one model, one particular way of training. But the fact is, if you fine tune on the data set, sometimes you will overfit, and I agree with that. Yeah, because like if you just fine tune on the reasoning traces and so on, you might do the wrong reasoning for other problems.
Yeah.
okay.
If you
Yeah,
look into Poet IQ, how they did it, you'll see they didn't hill climb or anything. They just, it's as clean as possible. So it's actually interesting how you're framing this. But the only question I ask is, what would be a real challenge for a benchmark, like in comparison to this paper?
I mean, there's a lot of different challenging benchmarks out there. Like the ARC challenge is one of them, ARC AGI. There's other benchmarks like humanities last exam and so on. But I think the main thing is not really the benchmarks. The main thing is more of like how do we want to train these models? Of course, we can use the benchmarks to gauge how they learn. Actually, I don't really like any of the benchmarks that we have out there. The benchmark that I desire the most is a dynamically changing benchmark, where one day you do step A and it works, and the second day you do step A, it doesn't work. Yeah, so that's more like, if you do API call, sometimes API doesn't work. Will your model be able to adapt? Yeah, so something like that is my kind of the favorite benchmark that I have because that mimics real life quite often. You don't get perfect outcome all the time. So none of the benchmarks I see in machine learning right now actually meet that kind of criteria that I have. So yeah, I think right now we are just trying to train for static benchmarks to make sure that it kind of works reliably. Moving on, we kind of need dynamic benchmarks. Yeah, that's my take on it. Yeah, Derek, yeah, you want to say something?
Okay. Yeah, I didn't want to interrupt Robert, but I wanted to comment on the benchmarks itself, but I think in terms of what you brought up, the dynamic benchmarks, I think the only way you can get like not 0% accuracy with any of these training methods, I think would be with like the model cannot just internalize the reasoning from an expert. I think the model has to actually develop an emergent behavior of like task decomposition and other abstract reasoning skills. I don't think the model can just keep internalizing all of these step-by-step trajectory examples. Now, my initial comment though, I think in terms of the static benchmarks, right? Like the ArcAGI benchmark, I think is a really good example, something that's not like code or math based, very like grammar based essentially, or logic based. I think what's going to happen, I think that the way you encode the rewards and do your state encoding is going to affect these results a lot. And I think that's going to have to do with like the more complex your environment is, I think the more complex your reward encodings are going to become. And I think what's going to happen is that your learning signal is going to get greatly affected. So the model is not going to be able to learn as easily or as quickly because there's so many more rewards and variables getting encoded. And now the model has to take into account this much more complex field and environment to learn from in terms of learning signal. So I actually think this benchmark is a good perspective, but I actually think my instinct is that the SRL into RLVR pipeline is actually going to get you a much higher boost, actually in a different context, like ArcAGI, because the ability to start off learning how to reason step by step, at least internalize step by step reasoning, right? And then prune that reasoning with RLVR and only focus on correct trajectories is actually going to boost accuracy on a benchmark like ArcAGI or something much more demanding than just like a math benchmark or a code benchmark.
Mm,
Because your issue is going to be with the model itself is going to have a good foundation, but it's going to consider correct and incorrect trajectories, which is fine if it's good at step-by-step reasoning, but at a much higher, more uh, difficult level, like ArcAGI, that requires, I guess I would say, like more abstract reasoning or step-by-step processing. I think pruning the trajectory so you only focus on correct trajectories with RLVR is going to help dramatically boost the performance more than it shows here in this benchmark. But that's my take.
definitely. So I await Google to release more data on this. I think they are doing experiments on it. We cannot tell for sure which is the best approach, but I can share with you my view. I think RLVR is not good. Okay, why? Because it focuses on reward. As you see, the reward is static. You get a reward every time you complete the task. But then again, if you want to have dynamically changing environments, if you impose a fixed reward like that and your model learns how to achieve this fixed reward, it's very hard to change the mentality once the reward is not achieved. Yep. So you have to spend many iterations to unlearn that reward. And that's why I don't think learning by reward for long trajectories is the best approach. It's best to learn step by step action prediction. Yep. So okay, if you know me and my previous YouTube videos and so on, like at my PhD research, I've spent my entire PhD trying to find a new method other than reinforcement learning because I feel that reinforcement learning, uh, you are too reliant on the environment too much because you have only the environment giving you the reward, and if something changes, your reward might change as well. And most RL environments don't cater for that because the environment is fixed. All right, so you end up overtraining to hit that reward, and something happens in the environment, You have to learn from scratch again. And sometimes it's even harder to learn because you have a flawed mentality that, hey, going this trajectory is good, but actually you need to go something else now. So I feel that SRL is a great approach because it finally goes to step by step. It finally learns how to match the action. And although it still uses reinforcement learning in some sense, that is minimal. It's more action matching than reinforcement learning. So I like the SRL approach. I don't really like RLVR. So that's my take on it. Of course, I'm happy to be proven wrong otherwise. Um, so I don't think this pipeline is ideal at all. So yeah, so that's my take. Yeah.
Sorry, I have a question for you. Just now you also commented you agree that SFT will overfit, right?
Yes, yes.
And so how does SRL address this issue? Sorry, I was absent for the first 20
No
minutes.
problem. I actually haven't covered that part yet. It's in the next
Oh,
slide.
okay,
Yeah.
sure.
Okay, but let's move on. Derek, you want to say something else before we continue? Because I just shot down RLVR, so maybe you might have something to respond to that.
Sorry, John. I think you're kind of breaking up on your end. But yeah, just to finish up the slide, basically you're saying that even with a much more abstract benchmark, adding RLVR after SRL and the training pipeline, you're saying it would hinder more than it helps. Like it may or may not prune the trajectories, but it's going to do a lot more harm than good, is what you're saying,
Yes.
with the final outcome reward.
It depends on the data set. If it's a static data set, maybe it helps more. But if we are talking about real world like solutions, like for example, a coding agent trying to call APIs and so on, having an RLVR output might actually hinder it. Because what if it calls like an API, for example, it calls Tailwind, um, or rather import a package Tailwind and the Tailwind is outdated, but it's being rewarded to output the wrong version because of RLVR, then that's going to take a
Oh.
while to change. Yeah, a lot of coding agents, I try to code apps and I have to reinstall Tailwind many times because I believe they train it on an old version of it. Yeah, so something like
Yeah.
that. Yeah.
No, that's a valid point because even with a coding benchmark or a coding agent, so if you put it through RLVR, it's gonna over prune the flexibility of the training process and the trajectories that the model is trained on, or I should say like rewarded for and likes, so that when it does runtime on coding, if it runs into even the slightest error, you're saying the RLVR makes it too brittle in its decision making, essentially.
Yeah. So if I were to go back to my earlier slide, RLVR is like you are trying to tell it that, hey, the solution to solve this maze is this, and this is probably the only solution you need to know. And then, what if one day the exit here is closed and then now your exit here is open? Then, you kind of need to unlearn this conditioning because the reward is still a one, you see. Now your reward is a one when you go here. You kind of need to unlearn this conditioning to go up. You need it conditioned to go down here instead. And if you were to train by reward, it is extremely hard to go to this door here. So if you're interested, you can check my paper on it. This is called Learning Fast and Slow. Later, I've slide on that if we can go to that. Yep. So this is basically I changed the maze itself, and using traditional RL approaches took very long to adapt, and that's why I'm a bit skeptical of RLVR because while I think RL is great for problems that don't change, like if let's say this maze doesn't change at all for your entire life, yeah, RL works. But in real world situations, that's not what's going to happen. And actually, I feel a lot of research right now is focusing on static benchmarks. We haven't really reached the real world adaptation of stuff yet. Coding agents is one step towards the right direction because in code, you are doing real world stuff because the modules change and stuff. And even in coding agents, I still find that you can only code well if your modules are not updated. If the modules change version and so on, you have problems. Yeah, so at least that's my experience when I'm using stuff like Cloud Code, anti-gravity, and so on. Yeah, so there's a lot of things that still need to be done in order to achieve real-world adaptation, and static benchmarks just don't cut it, right? So using RLVR makes the problem worse because you overfit to a certain way of doing things,
Sorry.
and that, yeah,
I really want to say something here. I totally can see where you're coming from. Like why, and your frustration, why it it doesn't work for your case. I believe that's also for most of us, that's the case. But you know why it works for those frontier labs or not? Because they can brute force it. For example, the maze problem, you say, oh, because you always reward the reward if the exit is on top, right? What if it's somewhere else? What if the environment changes? I believe what they are doing is simply brute force. They just train it on all kind of permutation of environment, and that problem goes away.
Possible is possible. But the reward, you see, the reward signal itself, if you just use a reward signal of 0 to 1, you don't really tell like the model much. Like,
Yeah, because
yeah,
you do want it to overfit, right?
not exactly, not exactly. In this case, using reinforcement learning to train LLMs, I find that it's a bit of a hit and miss. Like sometimes it is good if you want to output only certain things at all times. But if your data keeps changing, sometimes your RL approach might actually be detrimental to
Yeah,
training.
because you do not have enough data for that.
I guess if you have enough data, everything can be solved, right? Regardless of how you train it, RL or fine tuning, you will solve it.
I think I partially agree. Yes.
Yeah, so it doesn't matter what method you use in that case. Yeah, what we are talking about is we are talking about a limited data
I
problem.
see, I see. So
Yeah,
the setting will constrain ourselves in this limited data, limited compute and stuff like that.
yeah. That's more
Okay,
of a
sure.
real world setting. Yeah.
Okay, sure.
Okay, let's move on. Okay, so this is a bit of a more technical slide. I'm just going to explain to you how this RLVR, SFT, and SRL work in a more conceptual sense. If you're interested in the math equations, you can consult the paper, but I don't think the paper talks about all the equations. So if you're interested in how RLVR works, check out the DeepSeek paper that talks about GRPO. All right, so GRPO, Group Relative Policy Optimization, where they basically improve upon PPO, which is the proximal policy optimization, by changing the reward model to group comparison. Okay, so what I'm just going to give you, I'm just going to give you an intuitive view of how this is done. All right, so this is how it works. Say you have a problem. All right, let's just forget. Let me just delete away all this. So if I want to go technical, this is how I'll present it. I'm just going to go intuitive because honestly, a lot of papers have a lot of math, but that's not very important. The main thing is how the system works. Okay, you can always change the math to something else as long as your learning signals still feed back to the model, you still learn. All right. So let's think about, we strip everything down. We go down to the basic fundamentals. How does RLVR work? Very simple. You have a model, you have a problem. All right. You have a task or your problem, and then you roll out trajectories, and you have a objective scoring function. Okay, which in this case, like if it's math, it could be like the right answer. If it's code, you could see the right output. Yeah, so you could do very, very rigid and very verifiable rewards. Okay, so there's this huge thing about RLVR. Basically, it's just saying verifiable rewards that are objective or verifiable rewards. Okay, you then score your model, all right? You score the model saying that, hey, this trajectory maybe it solved the math problem. Great, the answer is 2, correct? Correct. Answer is 1, so it's wrong. All right, and what we do later is we basically take those trajectories that are correct, and then you pass this back to your model, and you tell your model, hey, repeat those good trajectories. Okay, because your reward is great for those. Go ahead and do it. And then you say, hey, avoid those bad trajectories. So essentially for every problem, as long as you have like at least one trajectory that is correct. Okay, and you could have multiple rewards here. Like you could have syntax rewards, like to reward output in the correct syntax, output form in the correct format. You could have a reward that says that if it's below a certain number of tokens, it's better. Yeah, different rewards, but this kind of rewards that you have the right answer already, you can then give that signal back to the model saying, well done, you got the answer. Okay, how you got the answer doesn't really matter. As long as you got the right answer, you get your reward. And I'll keep repeating those trajectories again. So I I feed back into the model itself. I train it using reinforcement learning um, to repeat those good trajectories and avoid those bad ones. But can you see the problem here? What if everything is bad? Can you imagine that? Like if I ask you to solve solve quantum gravity, for example, then no one can solve it, right? Everyone is stuck. Or like, show me that there are okay, well, basically an impossible problem, solve teleportation maybe, yeah. What if nothing can solve it? Then you end up with lots of solutions that are wrong, and essentially you learn nothing because you learn not to do any of them. But the thing is, even if you learn not to do any of them, there's no guarantee that you will find the solution because the solution might be so long. You might learn that, hey, it's not good to go this area, not good to go this area, not good to go that area. But what if there's like a billion areas and you can never cover the right area, which is like one in a billion or one in a trillion to reach the goal? Like, what if you never find it? Okay, so RLVR has that limitation because you might never find the right trajectory. Okay, it's not too much of a limitation if you have an expert model and you feed in the expert model as supervised learning to train your model, and at least your model have the right trajectories. So at least that's what they tried to do in this paper. But they found that if you feed in model solutions, sometimes it might make it worse off. Yeah, so that's the dilemma, you see. You have the expert model already, but you can't just fine-tune the expert model because sometimes it learns the wrong reasoning, it overfits. So even using SFT and RLVR doesn't work. Yeah. Okay, so let's move on to SFT. Okay, what's SFT? SFT is basically given a prompt, output the right tokens. And this is essentially used, okay, it's not exactly SFT is not exactly only for supervised fine-tuning. In fact, for LLM pre-training, we pretty much use the same idea. So it's like the cat sat on then there's a token here, right? So the right answer is met. And so we try to reward the output such that the softmax of the token probabilities is highest for the token met. And that's exactly what we do when we do LM pre-training. We try to match the tokens of what we see online. Okay, and this is called next token prediction. And basically your reward is based on whether your prediction is met. And I would say this is a good reward because it is very plentiful. Like you definitely know what the next token is, and you will definitely be rewarded for something. Very unlike RLVR, because RLVR you may not be rewarded at all. You may not get the right reward signal. This supervised fine-tuning, you always get the right reward signal. Okay, because you know what the next token is. And this is called self-supervised learning because you learn from the environment. And Yan LeCun is very big on this. I agree with him fully. I do think that observing the environment and learning from it is very, very important for a learning system because that's where you get the most training data. So supervised fine-tuning is basically given a series of tokens before, what's my next token? So that's now, I ask you what's the next move in Go and so on. Here you have a very rich and plentiful training system to predict the next token. Okay, which is great if you have like a short series of tokens you need to predict. But as you need to predict more and more tokens, you might get something that offsets it from the right trajectory. And if let's say you overfit it to your thinking tokens, you might think in some way and then execute it wrongly for a different problem. So there's some issues with SFT because although the rewards are rich, you can overfit to previous problems and you may not generalize to the next problem. So unless you have lots of data, then you might, as you say, use data to overcome the overfitting. If not, you will have overfitting problems. So how can we do a hybrid of both RLVR and SFT to make it such that you can learn with rewards, but you don't overfit too much to the next token, and that's SRL. Okay, SRL is basically instead of training the SFT and all tokens, I don't care about my thinking tokens at all. No training on the thinking tokens. I just take the output of the action, compare it with the model answer for the teacher. So this step one, step two are my like contexts that the model also has. I compare how similar this output is, and then I give it a reward based on how similar it is. In the case of this paper, the similarity is by token subsequence count, like how similar are the subsequences. So based on this reward, I can then do my GRPO. So they also use GRPO for this. I do my GRPO and say that, hey, repeat trajectories that give me the most similar action match for that substep, for that step, and avoid trajectories that give me bad least similar action match for that step. So it is very, very fine-tuned, a fine-grained reward because you give a reward for each step. And this reward is a little less dense than SFT because SFT you definitely get a reward. You know what's your next token. Here you may not match the model answer and then you may never reach it because I don't tell you the model answer. I only tell you how similar you are to the model answer using this reward. So you may not learn well for this, but at least it's not as bad as learning from all the way from the start to the end. You know those little light bulbs in the mazes we saw earlier? You still have a little light bulb you can go to in the middle of the maze or at different points in the maze, so you don't get lost too often. But you can still get lost. Okay, you can still get lost because what if you don't even output the right step here? Okay, you saw in the earlier slide, right? You saw in the earlier slide just now. Let me just go back to the earlier slide. You saw in the earlier slide, even with SRL, you don't solve the problem fully. Okay, you still can get lost here because you still rely on the model outputting something good for that right step. So we go back to the maze here. I just want to show you something. You might think that having this RL reward in the middle is good. But what if this maze here is still unsolvable for the model? Okay, have you thought about it? How? Right? Reinforcement learning only gets you so far. All right, so there's still a problem with SRL. Okay, so I think I will pause for a bit for questions because I know Robert wants to ask something already. So yeah, please go ahead.
So I'm agreeing with so RLVR basically it's solved by brute force if you really think about it. I think maybe we can agree or disagree on that, but that's how I see it. Now, SRL, right? That modularizes reward at training time. Have you ever explored applying SRL style stepwise constraints at inference time?
Yeah, I think at inference time you can also do it because when you do the model, you can output one step, then you output the next step, then output the next step. So at inference time you can still do SRL. I mean, it's not called SRL in that sense because you're talking about rolling out multiple steps and choosing the most. Now I'm just thinking, how do you do it at inference time? Because at inference time, your model only outputs something you may not have the reward, you see? Like this teacher response, you may not have it at inference time. Yeah. So if
It
let's say
would
you
be
want
like
to
a
talk,
governance
yeah,
layer.
say again.
It would be like a governance layer, like a multi-axis constraint, something, and rather than a scalar reward system.
Sorry, can you give one example?
Yeah, I guess like a thermostat. That's kind of a simple one.
Yeah. So I think at inference time, you don't have the teacher. Okay, because otherwise you might as well just use the teacher to respond to the query, right? Why use a student? So at inference time you don't have this teacher. So your reward is non-existent. So if you're talking about example like a thermostat, you still need a sort of teacher to kind of give you the right temperature, right? But I'm saying that there's no right
Well,
temperature right now.
you would need the environment, right? Just like Lan LeCun said, like you basically said that you would need the environment as a sensor or something.
Okay. So you want to give the environment gives the reward at runtime.
Exactly.
Okay, that's possible. Yeah. So basically, like if let's say you can run multiple API calls and then you see which one returns correctly, and then you just take the one that returns. Yeah, whether the API returns something might be your reward at runtime. Yeah, then I think it works. Yeah, it won't be called SRL then. It will just be called, I mean, you roll out the model multiple times, execute the action, and then use some rule-based method to rank which action is better, and execute the one that ranks better. Are you talking about something like that?
Well, kind of. I'm more talking about like a constraint. So for an example, the model can act freely inside the constraints, inside the walls, right? When you give it too much freedom, then you have an issue. So you have to build the walls first that it can act inside. So for an example, it cannot exceed one temperature, but it cannot exceed the other, but it has freedom to choose in between.
Mm. Yeah, I think it's possible to use rule-based constraints to govern the output,
Um,
but then I wouldn't
sorry.
I wouldn't associate this with SRL anymore. I would treat this more like a rule-based stepwise output. Yeah, so something similar in the essence. Yeah, so I think it's possible to do that if you already know the
Hey,
constraint.
Robert, can I chime in real quick, Robert?
Yeah, absolutely.
So I'm listening while I'm taking notes. Are you what you're referring to? I think it's a physics constraint neural network, which there's a bunch of papers on. So basically, the neural network has physical constraints put on its learning function, um, that allows constrains what it can learn and how it can respond physically on the parameters of the model. And then the model has room within those constraints to learn and optimize to its training data and its data set. So I think what you're referring to is just a physics constraint model.
Okay. Physics constraint model. Perfect. If you have any
Yeah.
white papers that you could send my way, because the way I look at it is at inference time, it makes a big difference than for an example, just training a model, right? Or hill climbing.
Right. What I'm
Like,
talking about, a physics constraint model, is just a training time constraint on the parameters of the model when it learns, so that it can only approximate a certain range of functions and its parameters, and it can't go beyond its boundaries. But you're just trying to implement the same idea at runtime, pretty much, which I don't think is hard. I think you would just put constraints on the outputs or on like the output layer of the model, like the what is it, like the decoder or whatever, the final layer of the decoder.
okay. That, yeah, just
But I'll
because
send
when you're thinking
you white
about
paper.
agent, when you're thinking about like multiple agents, right? It makes sense to
I
do it
mean, if
that
you're
way.
doing, yeah, if you're doing an agentic implementation, I think it would be I mean, the implementation would look very different, but like the idea is the same, where you constrain the range of motion of in this case, instead of tweaking parameters, you're tweaking the agents and their range of motion in their mathematical space, so they can only do a certain range of actions. Which I think you can kind of already constrain agents with like a framework, and they're only assigned a certain range of functions to choose from based on tool calls, but that's that's a different discussion.
Yeah. Okay.
Yeah, cool. I quite like the idea to constrain the outputs into acceptable formats. Although I do think that even with the constraints, what if your LM doesn't output it? So you kind of, if you had those constraints, you may want to put the constraints directly into the context itself.
Oh, interest. Yeah.
Because then, instead of just relying on the output to meet the constraints, you can just tell the model like temperature should be between 34 to 36. The chance of it giving you the right temperature is much higher than output any temperature. Then you constrain the output only for 34 to 36. Yeah, so there are different ways to do this. I think if you have constraints, you should model them into the input. Yeah, that'll be better. Yeah. So yeah. So I mean, this is a different way of doing things. Where you kind of limit the output for each step, which I think is great if you already know the limits. The thing is, in most real world cases, I don't think you know the limits. So this will only work for certain cases.
Why couldn't the larger model, like the teacher model, train the other, like how to build the constraints itself? Just a
Mm,
curious question.
I mean, if the constraints are always fixed, then sure. But sometimes it depends on what scenario you're in. And even if the teacher can train the constraints, sometimes the constraints might be wrong. Then there'll be another problem. What if your constraints are wrong and you can't solve the problem? Yeah, so there are
That's where
different
the
ways.
reflection comes in. But that's where the reflection comes in. Like you said, we could just basically use a vector or some level of rubric in order to figure out where it went wrong and then reflect.
Yeah, but you know the difficulty of this? The difficulty is sometimes you are wrong, but you don't realize why. So that could happen.
Sorry.
Yeah. So it's a great idea actually. Like using constraints to limit the output. Like for coding agents, for example, if you know for sure that you need to use Tailwind version 2 or something, you put that constraint inside there. And then if it's wrong, maybe you reflect on the constraints to see whether anything is wrong there. Yeah, I think that's maybe a two-tier approach to generation. First tier is to come up with the constraints. Second tier is to use the constraints to generate. That works. Yeah, here we are talking about every step. Like when we output every step, we kind of constrain on the earlier context. And I mean, it's very similar to how you output a long trace with SFT, like output a reasoning trace. But here, you focus only mainly on the action in the training. You don't train on all the thinking tokens. So yeah. So Robert, I quite like what you're saying about constraints, but allow me to go back to the main model itself because I don't think the model here is talking about constraints. The model here is basically saying that instead of training on the entire sequence itself, I just train on the action and see whether it matches. Okay, so allow me to go back to this. All right, we can discuss about the constraints one another time. And all right.
Sorry,
Uh,
I want to say something.
oh yes, go ahead.
But it's yeah more. I'm going coming back to the core idea here. So I don't think I don't think SRL actually addressed the fundamental issue that RLVR is facing.
Oh, finally, yes, I
Yeah.
agree with you. Yes.
Because you want if essentially what SRL is a form of doing distillation, right? You have to have the teacher model to give you the correct signal, whereas RLVR does not have the teacher. That's why it only has a very sparse reward model at the very end. And you rely on this, you assume this super accurate teacher model to give you the correct intermediate action for you to do RL on. That's the core assumption that it has, and it's not the first paper that come up with that. Actually, in fact, I shared the link in the group. Sorry, in the group chat. That basically the same idea, except that the paper did not use. I think they did not use the subsequence matching to form the intermediate reward, and it does not have a teacher model to give the correct action. But they somehow come out curated ground truths for the intermediate action. But the core idea is the same: is to do RL on intermediate actions. And this is better than DeepSeek R1's approach. If you have read the paper, they says they use a process supervised reward model to do this, and it's not good because it leads to reward hacking. That's because reward model is bad proxy for intermediate action. So here they actually come out with a very good teacher model to give you the actual correct action. So it's more akin to the LLVR setting where your reward is super accurate instead of just some proxy. So it kind of addressed the reward hacking problem. Yeah, but it all relies on the core assumption, which is you have a model is already capable of generating such intermediate action. Yeah, that does not address the issue with RLVR, in my
No
opinion.
problem. Yeah. So as we continue go through the slides, you go to my thoughts. I have a way to expand this to any trajectory.
Okay, sure, I love to
Yeah.
hear that.
Yeah. So you can see based on this approach, because you see many people think that RL is very good, and so this paper also tries to follow up with that. Uh, if you have talked to me before, I can tell you RL is not that great. And the reward here is to see the subsequence match between like how similar it is in terms of token matching between the teacher response and the response given by the model. Um, Actually, we are going very, very close. Okay, we are almost reaching fine-tuning kind of reward. Okay, what's lacking is like just do a fine-tuning of this matching of these tokens in this part here. That's what's lacking. We basically, instead of doing token by token matching, we do a reward here. But I always think that, why not just do the token matching? So, our SRL can also be reframed in a way that we basically train on the output tokens and we don't train on the thinking tokens. So over we avoid over committing to the thinking tokens, which sometimes might think in the wrong path, but we just focus on what's actually the output for that step itself. Why not? I mean, you saw in my earlier diagrams, I did not mention anything about RL here. I just say that given this prompt here, output next step, then this is the output. Now, I actually believe that you can fine tune like that. Yeah, you can just fine tune this as the input, and this is the output. Yeah, so I think you don't need RL, but of course, I haven't really tried it out. This is just my intuition. Yeah, because RL itself, if you were to condense down this entire step into a sequence matching and notes, okay, when we do this reward, okay, maybe it's best to go to the slide on how the reward is done. Note when we do this reward here is the longest contiguous matching subsequence. Basically, it's like the number of matching blocks in the two. It's very math here, but basically, if you take the input and the output, you see the number of matching blocks, then the length of the length of matching blocks over divided by total overall length. Yeah. So length of matching blocks times 2. Yeah. So basically, the idea is the ratio of match. All right. And you think about it. Okay, let's try to imagine that you are a child now. Okay, imagine you are a child and like you are only given rewards 0 to 1. All right. So let's say, for example, one day I say I am a cat. Then maybe I get a reward of 0.8 because maybe the model answer is I am a child. All right. Then like, oh, I'm not bad. I'm really a cat because it's 0.8. Then maybe I will put like he is a child. And then you get a reward of like maybe 0.7, 0.6, because like not everything is matched. And it's like, oh, that person not really a child, so maybe I would say that he's a cat. Yeah. Then maybe the reward is 0.3. So it's like playing this game called I don't know what's the game called. The game's called Mastermind, I think. Have you ever played before? Like you have to guess a code. Okay. Remember Mastermind, like you have four. I think different countries called different ways. You have four circles, and then you need to put different colors. Let's say, for example, this is red, this is green, and this is yellow. Now I will tell you like, oh, two correct, one incorrect. So like two correct places, one incorrect places. So you try to form the code word. Maybe the code word is red, red, yellow, blue. Yeah, because the yellow is incorrect, the two red are correct. Yeah, so you need to guess like what is the code word. In fact, here in the mastermind game, you have even more information than RL. Okay, if you were to play this game by RL, I will just give you a score of 0.8, and then you have no idea, or 0.7, you have no idea which position is correct, which position is incorrect. Can you see this part here? This is like playing the game mastermind, but you have no idea what position is correct and so on. Good luck, all right? Good luck trying to hit the right output. Yeah, because I'm not even telling you what the answer is for the substep. I'm just giving you a reward. And just now Robert also mentioned, like, okay, we should do the constraints and so on. But if I don't tell you the constraints, how do you even know how to output the constraints, right? Here, I'm not even telling you the model answer. I'm just giving you a score based on how close you are to the actual sequence of the model answer. And you know what if your model answer is like this? What if your model answer is this? The model answer could be like, let's say if you are talking about English, the model answer could be this is perfect. Or then you could answer like um it is absolutely correct. Hey, can you see this perfect and absolutely correct might actually mean the same thing in the same context? But let's count the number of matching tokens, shall we? 1. All right, so if I were to tell you that in this case, I will give you a score of maybe 0.1. And actually, you have the right idea, you have the right idea, right approach. You just didn't output the right token. And this is absolutely what I hate about the education system. Last time when I was doing science, um, I was given 0 for this question on like how does the body regulate temperature. The answer is homeostasis. Okay, where this word alone is the question is 2 marks, and the word alone is 2 marks. Okay, in my answer, I say that the body regulates the temperature by adjusting it according to a baseline, increasing it if below baseline, and lowering it if above baseline. Something like that. Yeah. So this is what I wrote in my science paper because I forgot the word homeostasis. I just don't remember stuff that well. And guess what? I got 0. I got 0 for this. I still remember this because I think I got the right concept. I just didn't get the right word, right? This, look at this reward here,
Sounds
right?
like your teacher is rule-based.
Yeah. My teacher is using reward-based learning. Yeah. Okay. I'm just giving the reward, given the reward when I hit the right words, right? And the problem with this approach is, okay, in this case, I'm even luckier than this reinforcement learning agent. I get to see the model answer at the end. I get to learn, oh, I didn't hit this homeostasis. So next time I learn. This poor RL model doesn't get to see the model answer at all. It doesn't see the model answer. It just knows that, hey, I got a 0. This might be wrong. And then it just deprioritizes the trajectory that reaches here. Can you see the problem here? Can you see the problem with reward?
Yeah,
It's just,
but
yeah,
it's a very easy fix, right?
yes,
You use a semantic based reward model. Or
even
just
semantically based reward problem, it only solves one thing. Okay, it only solves the matching of the reward. It doesn't solve how to get that reward.
but verifier doesn't care how to get, right? Why does it care? For RL
Correct. But the
setting,
thing,
it doesn't care.
the thing is, I'm only training it on SRL, which means that the only reward signal the model is going to get is the reward itself. And if the model is not able to get that reward even for that step, you get nothing. You learn nothing.
Even for SRL, you don't care, right? Because the reward model only needs to know the ground truth of the intermediate action. It doesn't care how the model reached there.
Yes, but what if it doesn't reach there? What if it doesn't reach a correct substep or correct step?
This does this paper address this issue?
Oh, no. Of course,
Oh,
take a look at the results. Okay, do you think this addresses the issue? Look at the results.
okay, so it's basically the same issue as RL, vanilla RL.
Yeah, you look at that. Like it can't even solve AIME, which is already like a full solve in GPT 5.2. Look, it only solves 20% of it, even with the best pipeline that they have. Like, so you can see the baseline model is here, like 12%. The SRL model is maybe 18%, 16%, maybe a 4% improvement. Okay, I can't really see. I have to look at the paper again for the exact, but you can see the improvement is marginal here. And I'm just trying to explain to you why I think it's marginal. It's because of RL. Can you see that the reward itself doesn't tell you how to get that reward?
Okay.
Yeah,
Mm.
so it's like trying to teach you stuff, but I don't even tell you the model answer. I just give you a score. And what's
Okay.
worse is that the score might be flawed because the score is based on matching subsequence. It's not even based on semantics.
Yeah, I'm just saying for semantic part, is there's a quick fix.
Oh,
But
definitely, definitely.
yeah,
Yeah, semantic. Yeah,
for the case where you actually want the to get the score based on if it's even wrong, but there's still partially true, then that requires such a strong reward model. It might as well be the teacher model, right?
yeah. So I'm saying that I think there's a easy fix for this, which is instead of doing a RL based reward here, just simply do a token by token prediction reward only on the action tokens. Okay, so actually there's a lot of this paper that I would like to dissect because I really like this paper a lot. There's a reason why I still chose this paper, even though I took a break on it for 2 months. I really like the way that they frame the problem, but I think they use the wrong learning method. Yeah, so I kind of want to end here for today because it's already 1.5 hours. There's still some more slides on how this reward thing works, how does it work for the output steps, and some other thoughts that I have. So maybe we'll continue this next week. But I'll just end on this slide here so that we can talk about maybe the next 5 minutes or so. If you have any questions and queries based on what we have discussed so far, what do you think about this reward matching thing? Yeah, we can spend maybe 5 minutes to talk about it before we end today. Anyone wants to say anything?
Okay,
Oh,
then can I continue my comment if
oh yeah. Go ahead. Sorry. Yes.
so I think I still think the way you propose still might not work
Okay.
because you are matching next token prediction, but how does it address the problem you mentioned whereby you have the wrong answer, but maybe it's partially correct. I don't think the loss from next token prediction can be reflective of that. Imagine
Neither.
like if your whole sentence is almost the same, it's just the final value is different, but actually how you get there is your rationale behind is very different. So on the surface, it look like the two sequence is very similar, but that so it give you small loss, but the small loss is not indicative of actually the vastly different rationale behind, right?
Yeah, I mean, you mentioned it correctly. Like, so even if a small loss, you get the right answer by chance, but you don't get the right thinking approach, you might reward the wrong thinking approach. Are you talking about that?
I'm talking about a negative case where you do not have the correct answer
Okay.
and you are proposing to use next token prediction. But I think it's still some semantic based verification is maybe more suitable here.
So you're saying don't use don't use a fine-tuning approach to do this part because this part might be wrong, right?
No, that's not what I'm saying. I think the intermediate reward is important. It's actually important because I agree with what you said. RL is, I think Robert also mentioned, very brute force, right? Because the reward is just so sparse. So we have to go into more subatomic level, if you will. Like you need to get the correct reward for the subsequence on the subsequence. But the issue is still the negative side. Like when you didn't get because RLVR they need a contrasting signal from the correct output and incorrect output to learn. If you don't have that contrasting signal, you cannot learn. Same here. But when the problem is when you have the negative when you only have the negative output, how do you extract useful signals, right? That's a problem. But what I'm saying is I still think semantic based ways to extract a signal is probably more crucial here because just by observing the next token prediction loss, that loss may not be as indicative of like the partial correctness in the negative example. Yeah.
I see. Why not we integrate both losses?
Yeah, I don't know. Maybe you can try.
Yeah, actually, I'm interested. When you say semantic token loss, do you have any idea how to achieve it?
I think the very straightforward, like naive way to do that
Yeah.
is just give that output to again. You really need a very strong teacher. Yeah, I can't. I feel like you can't get around that steps. You need a very strong teacher to understand why you get this output and why the output is wrong. Intuitively, how do you how do you get extract a useful signal from a wrong output? Is to know to have a very strong someone or something that has a very strong understanding of the problem itself, right? Then if with that even you know you can like even your output is wrong, but you still can see what where or how you get the wrong answer, but maybe some steps are still partially correct. I just feel like there's no way to get around this.
Yeah. So it's something like LM as a judge, right? Like you use the
Yes,
LM to
yes,
give a score.
that's a naive way. And I think I heard rumors like the Frontier Lab they are using this way to just to brute force it. Yeah.
Yeah, I also use LM as a judge quite often to, especially if the LM is good enough to solve the problem, you can use it to learn. But actually, what you mentioned just now made me think of something else. Not just the teacher can give you a score, right? If the teacher is good, right? Actually, the teacher can give you the criticism as well, right? Can give you
Yeah, sure.
improvements, right? So
Yeah.
all this is lost in this SRL format. So actually, what I was thinking is something like what Robert was saying earlier. Like you give a horrible, horrible way of doing things, and this is your context, and then you have the supplement it with the teacher's criticism, and this teacher is actually quite good at. And after that, you let the model itself, come up with the model answer. Then you learn compared to teacher's answer. Then you learn to see whether it's the same. So this is another way of learning. I guess this is called learning via criticism, I guess. Yep. So maybe you could have like all the unsolved cases, you criticize it, and then you try to see whether the model can solve it. You train this in the fine-tuning way, maybe what will happen is that the model will learn how to identify bad stuff, identify what criticism it should give, and identify the answer. So it might work. I mean, in real life, this is how it works. Also, we fail an exam, we learn from the answer, we see the criticism and so on. We learn from it and we improve. Hopefully, we learn from it. Yeah, you also can get stuck, but hopefully you learn from it. So
Would
yeah.
would we not need like some level of like some rubric or like a vector, some type of like even a currency system in order to weigh it? So for an example, we need some way to mathematically prove this. It can't be just based on outputs because outputs are interpretation based, right?
In
Like
this case, the
asking
output is verifiable because this is math.
yeah. So what can you explain that a little bit more how that would work? Because I understand what you're saying, but I don't see how that would be math, like how you could prove
Oh,
that.
oh.
That's all.
So instead of having normal like problem context, your context is the unsolved problem
Yeah.
plus the criticism. And then your output is the solved problem. So essentially you are giving it a new set of training data that starts halfway from the solution with a criticism, and the output is the solved problem. So you are trying to train it. Let me put in a visual diagram for you. So let's say this is a car, this is your start point, and this is your end point. Okay, so in RL, usually if you want to train like line following, you train on expert trajectories. One problem that they face in simulation to real is that if all your trajectories are like that, one day if your car starts off here, it doesn't know how to get back here. So one solution is you purposely do a random perturbation. In fact, AlphaGo they also did that. They do an random perturbation, and then you see how you can get it back to the trajectory of the correct trajectory. And this extra perturbations here, perturb starting positions plus the trajectory to get back is more robust for the learner, because then the learner knows, if you deviate from the main trajectory, how do I get back again? Because now I give it training data of how to get back. In fact, you might even do a fine tuning directly on this whole thing, because you have the model answer. Your model answer is the teacher's answer, right? You could get the teacher to criticize and get the teacher to give the answer like that, and you train that model. Your model will be more robust to being put away from the main path, and it still can get back to the main path again. Yeah, compared to just giving the model answer only with the model
Are
steps.
you like in layman's terms, are you basically saying like how to think versus what to think?
Yeah, yeah. I mean, how to fail and get back. That's
Okay.
fine. That's what I'm hinting towards. Yeah, I only thought of it because of what you said earlier on, where what if the step is wrong, right? So this is exactly the kind of training data we can imbue in the model to make it more robust by giving it like an example or a scenario where the previous steps are wrong and try to guide it back to the path. And I think this will make the model more robust, definitely. Yeah. This is something that maybe we could write a paper on. I think this actually might work because a lot of benchmarks they only focus on the correct trajectory. But it's also important to learn why we fail as well.
Nice.
Yeah. I mean if you're interested, you link up with me, we can write something. Yeah. I think
Absolutely.
this is something that I see promise in, because in reinforcement learning, the exact same thing where you perturb the starting position and get back on track works. It works for driving. Yeah.
Well,
So
yeah, like liquid neural networks, if you like I've studied a lot of liquid neural networks and this is what they do naturally.
yeah.
And it's a very yeah, and basically it's interesting how though, but I don't understand though, like for me you're saying the mathematics of the criticism, that's where I'm a little bit lost. Like how
So the
I don't
criticism
understand.
here is going to be in
Yeah, that
text.
mathematics.
It's not a score. This is going to be in text.
Oh, there's no score there.
Yeah, the score is only if you want to use SRL, then you have a score maybe of a 0 to 1 that you use a LM to output. But if not, I mean the LM also can output based on category. You can say like very similar, similar, not similar. You can give some definition and then you can translate this to a score in SRL. But
Yeah.
what I'm talking about here is we are talking about text feedback. So text feedback, you can put that in the context as well and use that text feedback to come up with the answer.
Interesting.
Yeah,
So
so
yeah,
mm,
go
yeah,
ahead.
sorry, continue, please.
No, it's interesting how you're saying that, because it's instead of for an example, half the time, like this is like another single thing that I learned. Like when I'm talking to the model from a context base, if I talk to the model, it will always, try to answer a question as if it was a human. That's its like first go to, because it's trained on human data, right? So it tries to answer that. Once you restrict all of its rights to think like a human, it gives you totally different answers.
Yeah, definitely, definitely. So the context does matter. So you can make the model more robust by just training it on more context. And I think this is something that's lacking right now. Yeah, this pipeline. So yeah, definitely this is quite interesting. I mean, I wasn't thinking in this line of approach when I started doing the slides, but I see merit in this. Yeah, I see merit in this approach.
Cool.
Cool. Okay, so I think we'll be ending here today, and I just want to say that eventually we'll come to like one of my other papers that I talk about. I do believe this is still unimplemented in deep learning, and I want to implement something where you can, based on trajectories that you already have, and you learn from your own trajectories. Even you succeed or fail, you still have something that you can learn because you have a start state, you have a goal state, and you just simply learn the next action. And that's all you need. You can learn anything in that trajectory of yours. You can start anywhere in your trajectory and anywhere, and you just learn the next action. Yeah, so this is what we have seen in mice, in hippocampal replay. This is what we do. We have the replay running forward and running backwards, and I kind of guess that we do some form of goal-directed learning in our heads because of this. The typical literature in neuroscience will say that this is reward-based learning because we are trying to learn like that this trajectory gives you a certain reward, or like you do a temporal difference learning and learn the reward. But what I'm saying is that we are probably just learning the action. Yeah, so this goes very well in what SRL is trying to highlight, that we are learning the action. So I'll touch more on this because I still believe in this. This is an idea that I created 3 years ago now. Yeah, so this is something that I believe quite strongly in, that will surpass reinforcement learning. Or reinforcement learning will still be useful for some things, but when you talk about trajectory learning, you may not want to use RL for it, for the very reasons why I mentioned earlier, that RL does not give you a very good learning signal, right? So just give you this slide, and then we will talk more about how we can lead to here with some of my other thoughts next week. And yeah, happy to see you all again next week. Okay, okay, bye, Brad.